hope you enjoyed your coffee, and let's see if we can do some weird mathematics and see if we can indeed prove that 42 is prime. So I promise it will not be too mathematically technical. There will be a bit more like code and that kind of technical things, but I hope at least everything should be more or less readable with a general security or computer science background. So a bit about me. Roughly 2 months ago, I finished my PhD back in Belgium in Leuven. I worked on all kinds of privacy-preserving technologies and protocol thingies. So from multi-party computation to zero-knowledge proofs and related things. These days, I'm still doing cryptography things, still doing protocol things, but now employed at 3MI Labs in Belgium. And I'm essentially a bit on the boundary between this research life and the more mathematical stuff and how everything works out in practice. So somewhat relevant, both because there's people from organizers here and because just the CTF experience gives a lot of extra background and tells you a bit what to look at when you're reading code with a security mindset. I play with organizers. My personal website is also on there. And so roughly the overview for the rest of the talk is like this. So first, I will have to take you a bit through a more theoretical mathematical thing so that you at least have the background of what is a proof, what is a zero-knowledge proof, building up to, okay, so with a zero-knowledge proof in mind, what is now a zero-knowledge virtual machine, and why do we care, why would we want those? From there, we can dive a bit more into the specific zkVM where we can demonstrate the bug in. And so there's a few bugs that we can work out there. There's a bit of a bug, non-bug, depending how you look at it. First, as a warm-up, and the first thing that we found while reading through the code, then we take a little sidestep at some funny, maybe not a bug, maybe a bug, depending on how you look at it, thing that just happened in their code base at some point. And then we can slowly ramp it up to actually exploiting the entire thing. Due to technical issues with trying to connect my laptop to the presentation and just probably a general lack of time if I look at the duration of the presentation. Actually demoing it will not exactly work out, but there's a link with a blog post and there's a link with the code that you need to actually reproduce the findings. So what are zero-knowledge proofs, what are zero-knowledge VMs, and what are proofs in general, maybe as a first thing. So if you hear proof, let's maybe look at a quick standard example of what you might see as a proof when you're doing just general mathematics, right? So recall that we say, okay, we define I as a square root of -1, so that we can just apply some rules of working with square roots here, and so when we multiply two square roots, we can say, well, that's the same as multiplying the thing under the square root, and suddenly we arrive at -1 being equal to 1, and with only a bit of work there, you can turn this into what is equal to 0, and from there it's not too hard to see that 42 is indeed equal to 41, and hence prime. Just as an example, already just irregular proofs, you have to be very careful what exactly are the sort of steps that you accept as this is valid within a proof, and to give a first intuition of a proof. So a bit more philosophically speaking, a proof we can say is anything that convinces some verifier. And in the cryptographic context, we'll often think of a proof more in the sense of a protocol where there is an interaction between the prover and a verifier. And so the prover does not necessarily just send a single string, a single blob as this is a proof, you can verify it, But there can be some back and forth between the verifier, and the verifier can ask questions or ask the prover to clarify something, for instance. And so to formalize this a bit, what we look at is usually 3 properties, or well, 2 properties for proofs, and then a third that is often interesting from a cryptographic point of view. So the first one usually comes fairly easily, and that is completeness. And with completeness, what we want to say is, okay, I have something I want to prove. I know that it is true, so I must be able to produce a proof for it within this proof system. Generally, by construction, this simply works, and most proofs, well, most classical proofs that you see when you're reading a paper that defines the proof system will go over this fairly quickly and say that it follows by construction. The more tricky ones, both in terms of construction and in terms of actually getting security, are the next 2, where on the one hand we get the soundness. And so the soundness kind of gives us security from the verifier's point of view, because they want to know that, okay, if this protocol that I'm following says that the proof is valid, if the output is, yes, this is a valid proof, then I want to be sure, potentially up to some minor probability, that this is indeed a true statement, a true fact, and not that -1 is equal to 1. The zero-knowledge property looks more at security from the prover's side, where the prover might have some secrets embedded in his proof. And one classical example here is looking at signatures. So thinking back on the previous presentation, there was a signature on the microcode updates that had to be checked, and so there's a private key for those signatures, and you want to prove something relating to that private key, for instance, but of course you don't want to reveal anything at all about your private keys, or suddenly you can do arbitrary microcode updates, which tends to not be very great. So we formalize this even more usually in the sense that the verifier should learn nothing at all, even like 10% of a bit of knowledge that the verifier would gain is already problematic. So knowledge comes in a few ways in these zero-knowledge proofs. And so on the one hand, we have zero knowledge. The way we tend to define this in order to prove things about it tends to be, okay, so we have this protocol execution, and we can make a transcript of the prover sent this, the verifier then sent this, and so on and so on. And we want this entire transcript to be simulatable, in the sense that if the verifier did not have this aspect of sequentiality because they participated in the protocol, they could have just come up with the entire transcript themselves. And so to an outside party, to a third party, you can present the transcript maybe, but that's about all you can do, and the transcript you could have made up yourself. So you kind of need this interaction, this sequentiality for the verifier to be convinced and to get zero-knowledge properties out of, and mostly soundness as well. On the other hand, as an aside more, because it's not too relevant, there's also the concept of a proof of knowledge, which is kind of the opposite side of knowledge, where you want to ensure that if you were able to prove something, then indeed you know a certain value. You know, for instance, this private RSA key. Now, interaction is annoying. For one, cryptographers are not always the most social creatures, or mathematicians, or whoever, computer scientists if you want even. So we kind of want to remove this layer of interaction, but as I said, the interaction is kind of baked into this concept of a proof as a protocol, so you need to take that into account somehow and try and get rid of it. So we want to be able to just produce this single proof string that we can send, and so what we do is, in a lot of cases, we look at the verifier and we say, okay, well, in this protocol, all the verifier really does is generate some random numbers, flip some coins, and then send those coin flips publicly to the prover, and all that really matters is the fact that the randomness was generated after the prover sent their previous messages. And so this is where heuristic comes in for a transformation that says, okay, well, we have this verifier, but all it's really doing is making sure that something random is only sampled after some message has been produced. So what we can do instead is we produce this randomness as the hash of a message, and then assuming certain security assumptions on the hash function, the prover cannot predict what the random coins will be before generating the earlier messages. Now, from a security perspective, this has gone wrong in many, many, many different situations because it's very easy to forget to include something into this hash, or you might not include the statement you're actually proving, and suddenly you can transfer a proof from one statement to another, and even though it's valid for one statement, it's not for the other, but you still accept it in a non-interactive setting. The problem with this is that as a cryptographer, it's very well known and well understood to say, okay, we have an interactive protocol, so of course we have this heuristic, the Fiat-Shamir transform, so of course you can apply it and turn this into a non-interactive protocol by yourself if you want to. We're writing a paper, that's all we really need to care about, and then when you start implementing things, everything breaks because you forgot to make sure that you have a unique serialization of the data you're hashing, and suddenly you have two different sets of inputs that give you the same hash, and all hell breaks loose. That is mostly as an aside, because we'll not be abusing the Fiat-Shamir transform later on in the actual bugs here, but to give you some idea, there's a lot that can go wrong when you're looking at implementation, and there's a lot of things that you really need to pay attention to that might not be as much of an academic interest. Right, so what are then these non-interactive proofs often used for, and what are they advertised for, especially in the really exploding area where a lot of this development is going on, is in the context of a roll-up. So if you look at a blockchain, you have some current state, and you can make a transaction as a user of the blockchain, and that does some update to the state because you now have less money, someone else has more money, and that gives you some change. But having to verify all of this and all of these transactions individually takes up a lot of time, and you're in a distributed network, so suddenly all of the nodes in the network have to do the same validation. Instead, if we can make this kind of proof, and we can make the proof what we call succinct, being it's something very short, and it's a lot more efficient for the verifier to verify the proof than it is for the verifier to get actually a check over the entire statement being proven, then we can accumulate a lot of these transactions into what we call a roll-up, and then everything the nodes in the network need to do is to verify the single rollup, and suddenly they have a few thousand transactions verified rather than having to do them all one by one. Now, these things are called zk rollups, even though the fact that they're zero knowledge tends to not really matter that much and tends to not be used. So what happens is people start a new business. They say, okay, we'll do some layer 2 rollup network, and we'll use zk rollups for this. And then end up not caring about the zk, but marketing it as zk and having an implementation where things are not zk, and then inevitably at some point, someone will try to use it for something that it was not built for and assume that there is some form of privacy on your inputs. But hey, it's zk, you can trust it. It's cryptographically sound. All right, so a bit looking at what things we can prove, and don't worry too much about the exact structure or the exact mathematics on here, but we can see that one of the common things that we encounter as a protocol structure is this three-message protocol, which we often call a sigma protocol, where you see, okay, the prover commits to something, the verifier flips a coin, sends the challenge, and then the prover responds to that challenge, thereby proving in some sense up to some minor probability that they indeed know the value they're talking about. The problem with this specific protocol is that we're looking at a fairly restrained class of statements, namely those of the prover saying, I know a pre-image of a certain function having enough structure. So that is not great because it's fairly limited in the things you can actually prove. It's really nice because you can build signature schemes out of it, but its utility kind of slows down when you're looking at more of an application side and a roll-up side, for instance. So what then happened on the research side is, okay, well, we want to make a general statement, so we will start constructing proof systems that work for arbitrary arithmetic or Boolean circuits, kind of like the circuits that are up to a high level powering your computer and that you might try to voltage glitch, for instance. And so we can describe whatever computation we want as a circuit here, and sometimes you can add extra gadgets like a square root, but overall, the idea is that with just being able to prove additions and multiplications, we can prove everything we want, as long as we can write a circuit for it. From circuits, then, there were further generalizations and further developments to different arithmetizations, but generally, this is how things evolved. Now, the problem with such a circuit is that writing a circuit for every application where you might want to prove something becomes not only tedious, but also hard, and you need to be very careful that you're constraining things properly and not doing assignment instead of a constraint. And there's a lot of bugs and a lot of extra manpower that can go into actually making all of this work. So then the next step in the evolution is, okay, well, we assume that, or we experience that writing circuits is hard, so let's now write circuits and just write code instead and bring this closer to your everyday developer that doesn't necessarily know a lot about cryptography or zero knowledge proofs. So let's write everything in Rust. And now we want to write a program in Rust of which we can verify the execution, that it was a correct execution according to some CPU model, and that certain outputs were correctly attested to or computed by the circuit. So that means that now we start writing entire custom emulators for WebAssembly, RISC-V. RISC-V is fairly popular among the current generation of zkVMs. And that brings advantages with it, because to the general developer, you already have a lot of the infrastructure in place to go from a Rust source program all the way down to some machine code. And you're targeting RISC-V, which we have existing tool chains for, so really all of that works out nicely, and then we just need to write our constraints on the CPU correctly and make sure that we can generate these proofs. So for instance, the code we can start writing now, and we can slightly abstract over this, but we can start actually writing more or less readable code that, in this case, calculates the 10th Fibonacci number mod some prime number. And we just say, okay, well, after 10 iterations of Fibonacci, this is my current state, and I can prove this to you, and you don't have to recompute everything to verify it. So zkVMs are a good idea, they are definitely interesting, but of course, while implementing them, we need to be careful. Now, a bit more architecturally technical, how does the SP1 zkVM, the one that we look at in particular from now on, how does that work internally? So first off, there's very roughly, and this is a lot of debate if you look at more academic cryptographers, but very roughly we can split succinct zero-knowledge proofs into two categories. On the one hand, you have the snarks. On the one hand, you have the starks. So snarks have the advantage that they're really, really, really short. As in, you have snarks of a few hundred bytes, maybe. But they're really costly to compute the proof for, and you might have downsides such as you need some trusted setup, or you need some even application-specific trusted setup, and they tend to rely on computational assumptions that are not secure against quantum computers. But as long as there's no quantum computer, we have the advantage that they're really short, so if you need to send something on the blockchain itself as a proof, they're really good for that. Starks, on the other hand, rely on more the symmetric key assumptions, and so they mostly rely on hash functions. We know that those are secure against quantum computers, but the downside is they're a bit larger, so they're not as good for things we might want to send on the blockchain. So what we can do then is introduce a few different types of proofs, and so most of the time we'll stay within these Stark proofs that are computationally not as costly, and then if we think it's worthwhile or if we want to send something on the blockchain, we can finally transform those into a very short snark, and so the first two here are the Stark proofs, and then the last two are two different snarks that you can target, which each come with their own trade-offs. So as a diagram, during the execution, we start off here with our core proofs, our shards, and what that is essentially is you look at the trace of the execution, so you just run the program in your emulator, and at every point you look at, okay, here my registers had these values, I was executing this instruction, this was in memory, and so on and so on. But once you're starting to run larger programs, it takes a lot more time to compute a proof over the entire program. So what you can do is you just halt the program intermediately after a few million cycles, say, and you say, okay, well, we'll prove this shard, this part of the execution separately and continue on, and then later on we need to combine these shards in new proofs. So we start with our shards, we prove that they correspond to correct execution, and we add some extra metadata to it to make sure that we can link them together nicely. Then from there we can start combining things, and we can get a final compressed Stark proof that then can go, if wanted, into something that is nicer to turn into a snark, and then finally we can turn into a snark that we can send on the blockchain. Now, these things are kind of weird because essentially what you're doing is you're verifying a proof, and then you're producing a proof that you correctly verified the proof. So this is what we call a recursive proof. And so as we'll see, these different types of recursion each have their own implementation in the SP1 zkVM, which each duplicates some of the logic, and then, of course, problems can start sneaking in. So what's the kind of data that we need alongside, well, the actual proof, of course? So when we're producing, or when we're looking at this recursion, we have some set of shard proofs, which is the things that we're starting our recursion from. We have some extra challengers that are this Fiat-Shamir heuristic starting to pop in, that we keep track of, okay, is this complete? Is this the final shard that ended the execution with a halt of the entire program? We keep track of, is this the first shard? Do we need to look at setup? And then we keep track of, are we actually looking at the right kinds of recursion? Right, so what's in a public value? Because you can see, I'm not sure, or we also keep some public values alongside the proof, and so this keeps, among other things, a hash of everything we committed to. So everything we said, okay, this is now a public output. Of course, that might be a lot of data, so in the proof, all you do is actually say, well, this is a hash of all the data you committed to. I'll provide this data separately, or you can get it from somewhere else, and then you can verify the hash, and you can verify that the hash is correct with the proof. We also keep track of the starting program counter of a shard and the ending program counter of the shard, and we keep track of things like, okay, well, what executed program exit with, what was the digest of our memory, how did our memory look before and after this shard executed, and so we start seeing like the previous thing that needs to be linked to the next thing in these merging recursions. So as the first thing that we found that arguably could be a proof, arguably could be a bug, arguably is just a peculiarity of the choices made. When we compare what a computer is executing versus what we care about in zkVM, we see that the computer has this very in-depth idea of cache hierarchy, and memory is expensive, and if you need to go to main memory, you've already lost a lot of time. On the other hand, in a zkVM, because in a certain sense, because it's zero knowledge, you don't really know which execution you're executing, or which instruction you're executing at which time. In a certain very superficial sense, you need to prove all executions or all instructions at the same time. So it's not that an addition is suddenly far less computationally expensive than a division. Everything is roughly the same cost, including everything might potentially incur a memory access. So the memory cost is always there, and instead adding more registers, adding more caches just means that we need more things to take care of while we're proving things. So instead the decision here is made to say, okay, well, now a register essentially just corresponds to a special value in memory. So in a RISC-V architecture, there are 32 registers, so addresses 0 through 31 are now reserved as registers. Additionally, however, in RISC-V, there's this idea that the 0 register is hardwired to the value 0. So whatever you write to it is discarded. Whenever you read from it, you get a 0. Now, what happens when suddenly you're writing to the null pointer? You're writing to the 0 register, and at this point, this memory, as a memory access, this is not constrained to just write a 0, whereas as writing to the 0 register with an instruction that is a register write does make sure that no write happens. So as a first proof, what we can do here is, okay, we say, well, we do a primality test here and we commit to the number at its primality, but additionally, why not, let's do a single byte write to an arbitrary address of choice of the prover. It's a single byte write. What's the worst that could happen? And of course, you can argue, and there are arguments that having a null pointer write is not that exotic to come across, and all sorts of supply chain attacks might apply, that somewhere deep down you can come across this kind of accidental write to the null pointer. But if we write just a single byte to address 0, just a single one, suddenly your compiler, who in the compilation of this isPrime function thought, well, return false, yeah, that's just moving from the register that's always 0 to my return value, said, okay, well, is prime returns false, so move from the 0 register into the return value. And now after this write, our 0 register has a 1 value, and what was false is now suddenly all true. It has downsides in the sense that a lot can break if you write to the 0 register, so getting a proof going is not always easy for arbitrary situations just like that. And part of the argument why this is not a bug is that RISC-V is a family of architectures, and if you define access to these register memory locations as undefined behavior, well then, obviously you're getting undefined behavior when you're writing to them. On the other hand, there's a lot of money going on that is protected by these zero-knowledge proofs, so if you can avoid this soundness problem, maybe it's something that you actually want to add an extra constraint for. Right? And so remember when I said that zk is a bit of a buzzword, and we really care about succinctness for a lot of the applications, but we still put zk in front of it. So we want the verifier to learn nothing at all, especially not about our private inputs. So now this, at some point, everything in this talk has been fixed in newer releases. But at some point, this was in their code. This is not a finding of us. This is just something I came across, seeing commits addressing it at some point. So the SP1 standard in type here is the input that the prover provides to the emulator. SP1 proof with public values is kind of like the name implies, a zero-knowledge proof with the public values, and the public values, again, being like the things that the program output and everything that we looked at before. And then there's a version string in there, but, you know. And then there's the prover's private input in the proof. It gets worse. At some point, they fixed this, and they had a PR that said, okay, well, we removed this everywhere we need it. And then about a week later, slightly over a week later, there was this new PR that went, okay, well, new feature, also removes break-in changes to the SDK from this commit because it broke the prover network. The prover network, just for short, is a network of provers so that you can outsource the more computationally costly proof generation to other people. All right, so then we can start moving on to the actual problem, bigger bugs that were proper bugs and not arguably RISC-V peculiarities. So first, let's look a bit at what these output commitments actually do, right? Because we're running a program, we want to say, okay, our output was this. We looked at this number and we determined that its primality was true or false. So what happens internally when you call this commit function, some other things happen, and then you take a running hash of everything you've been committing to. And I'm not exactly sure if it's problematic or not, but for instance, I don't think this running hash does quite strictly look at domain separation, so you might be able, again, to find colliding sets of inputs if you play around with the types a bit. But we take just a running SHA-256 hash, and we update it with the data we've committed to. And at this point, we've proven that we correctly executed this hash, but we're not tying it into the public values of the proof yet. So when we get into this function syscall halt, which is not what runs when you call the syscall halt, but which is what runs when you return from main, you start looking at, okay, well, now I will take the final output of this running hash, and I will make some syscalls to the emulator and to the proof that these are the final values of the hash, and so we split it up into, I think it's 8 32-bit words that we each commit through a commit syscall. And then when this commit syscall is made, what happens is we have some checks, and they say, okay, we have, in the prover's view, we have this known public value that we assert the hash is, and the program makes this syscall, so we can check that those two things match. Everything there is fine, except the problem is that we only do these checks on the public values hash when this commit syscall is made, and when is this commit syscall made? When we return from main. So, of course, we can start thinking, well, what if we don't return from main? Again, this is arguably not the most dangerous kind of program, because a lot of your security still depends on the program itself that you're proving, and explicitly calling halt here somewhat violates the assumption that you're dealing with, or that you're executing correctly according to the model that the prover expects, or that the verifier expects. But it's not unthinkable that you can say, well, we're done here, so we just call syscall halt, which is completely different from the syscall halt function from before, and we just stop the program here. We stop the program exactly at that syscall, so in particular, none of those commit syscalls have been made, and there are no constraints at all on the hash value we're committing to, meaning we can change it to whatever we want. Now, by itself, yes, interesting, but not the greatest way to really end our program. So what else could we look at? I looked a bit at, okay, now what if instead of calling this halt syscall, we see if crashing is an option, and there are a few ways we might be able to crash, and one of them would be like a Rust panic, or we could call the unimplemented instruction in the RISC-V assembly, but overall those don't really work out because unimplemented, ironically enough, isn't completely implemented. A crash might also exit with a non-zero status code, and the non-zero status code then does not generate a valid proof anymore. So what can we do? Well, remember how there are all these different kinds of recursion and different kinds of proofs, right? On the verifier side, the verifier wants to be able to verify each of these different forms of proof. So there is verification logic in a few different places. There's the plain verification logic, which is just, okay, I send these core proofs, just a sequence of proofs of individual shards. It's large, but it's fastest to compute for the prover, so maybe it's good enough. And so you've got the plain verification that does this. And then in the recursion, there's a different verification logic that looks at, okay, I need to do the verification, but I need to be able to prove this. So I need to bring in some more machinery. I need to do some extra work to actually generate this proof of verification. And there are different kinds of recursion, so that code is also repeated a few times, or those constraints are repeated a few times, and then things can go wrong. So if we look at this piece of code from one of the recursions compared to this piece of code, well, I've trimmed it down a lot because both of these functions are several hundreds of lines of code each, but there's one fairly important line of difference that you can spot in the way I cut it down here, and that is this assert complete, which is a function that takes care of all the constraints you get when you say, okay, well, this, when you say, now this is a complete program. And when it is a complete program, you want to assure things such as, well, my program counter has been set to 0. I want to make sure that my exit code is 0, all these kinds of things. But overall, in one single of these recursion verification paths, that assert was missing, which in turn means that there is no check that the program actually halted where it should have. We can just halt early, and so early might be as soon as you enter main. I think I tried halting slightly earlier in my proof of concept, and then somewhere the initialization still wasn't entirely there, so I just decided to break on the address of main instead, and that made everything work. And then you just generate a proof of your execution up until that point. From there, all that is left is just going into the right recursion where this check is missing, and suddenly you have a valid proof that the verifier will accept that you executed a program, but the program was not entirely executed. Now you combine this with the previous thing where if you don't exit the program properly, there's no check on the committed values, and suddenly you can prove anything you want because you can be committed to any output you want, and any code that you didn't actually end up running because you stopped early, well, it's fine. So I guess the overall takeaway here is that this kind of cryptography can be really cool and really interesting, especially if that's the kind of thing you're into, but the implementations themselves are still very tricky and dangerous to actually get into, and you don't always need this kind of deep cryptographic knowledge to start looking at this code and start looking at what could go wrong. As a general security practitioner, if you have a bit of CTF experience or a bit of general offensive security experience, you're reading code and there are points where you feel that something doesn't quite feel right, and maybe that's something you can look into, and in the end, the main exploit here that I talked about just needs this bit of system thinking and how things interact to get to a big end result, and I think I can't show it because of constraints, but like I said, but the overall proof of concept is maybe 10 or 15 lines of code changes to prove that 42 is indeed prime. Additionally, there's a bit of a weird dynamic here where the companies and the people developing these kinds of technologies, they want to make money, they're getting venture capital, and they want to push a product, and they want to get traction with their product. On the other hand, this is the kind of use case for their product where a lot of money can be bound up in it, because once you start faking proofs for transitions on the blockchain, suddenly all of the money that is secured behind those roll-ups becomes vulnerable, because you can suddenly prove that, oh yes, you gave me $5,000. Thank you. And so, in that sense, there's more to be found, I'm sure, so feel free to have a look. Yeah, demo won't work because, well, time and computer stuff, but there's a blog post behind that QR code that also includes a link to the proof of concept implementation.